Hello, everybody. Thank you for having me again at CCC. It's always a pleasure to be here. Unfortunately, we're still remote. I really hope we can go back next year to like an in-person conference. But as I said, it's always a pleasure to be around, and I'd love to come back. So today we're talking about a slightly different topic. So people that know me, they know that I'm coming from a strong Java background and that I've always been into development. But there is like a slightly and guilty little pleasure of mine, which is actually Postgres. And today we're going to talk about PostgreSQL as a time series database because there's a couple of different ways on how to do that. And I just recently joined a startup that is an extension on top of Postgres and implements time series from my perspective the way it should be, like no configuration necessary whatsoever. But let's just jump right into it, right? So today's topic is PostgreSQL, the time series database you actually want, right? So I'm Chris. I'm a developer advocate at Timescale. The Twitter account is TimescaleDB if you want to follow that. But for most of you, you may know me from a couple of different companies. Most people know me from Hazacast, where I've been for many years, and I love Hazacast. It's a distributed hash table implementation plus many different things on top of that. I've been with Instana for a couple of years, which is an observability tool, and from there on, I actually went on to my own startup, and we built a system. We built hardware and software to measure temperature, humidity, CO2, ammonia levels, all that kind of stuff in animal barns. So all these kinds of IoT metrics, and that's how I got into time series. And that is also how I got into Timescale. Well, guess what? I really like it. So in the past, I've always stayed with the companies where I really loved the products. It was the same thing for Hazacast, it was for Instana, and now I'm at Timescale. Anyway, I'm deep into developer relations. I've been doing that for a couple of years. I've been really deep into performance engineering. That is the actual background that I'm coming from. And in general, any kind of back-end technology. But the funny thing is, most people kind of leave the room with my favorite topic, which is always like anything performance related, like garbage collector optimization, in general performance optimization. That's like where people actually started like, oh, he's crazy, let's not talk about it, let's not talk to him, right? Anyway, anything performance, and time series is certainly about performance if you need to implement time series databases. So I think let's get straight into it. I mean, I'm talking about time series all the time, but what is a time series? I mean, maybe you're new to this, and I just want to make sure that we're all on the same page, right? So I brought a couple of examples on what a time series looks like, or what time series data looks like. So in general, all kinds of financial transactions, for example, are a really good example for time series data. So right, you have a transaction timestamp, you have some data around that, like account number, like the amount that is transferred, the receiver's account number, and all this kinds of stuff. Also, stock prices, same thing. You have time, you have a symbol, and you have a value, whatever that is, right? And there's a lot of them. IoT metrics, that is what we did, right? IoT metrics is this, like, you collect a lot of data and you need to make sure that the data is assigned to its timestamp when it was recorded, but also to the specific sensor it was recorded off, because two temperatures can mean completely different things, so you need to separate those. Any kind of observability metrics. As I said, I've been with Instana, and we've been deep into observability for anything. So any kind of metrics, no matter if it's Prometheus or if it's collected by Instana or any of the other tools, these metrics only make sense if you have a timestamp and a value, and well, instead of a symbol, you have a metric name or something assigned to it. Service traces, right? How do services communicate with each other? That's kind of the same thing as observability metrics, but in this case, you collect not the like actual time metrics, like how much time did a request take to response, but you collect the information like, hey, at that point in time, service A actually called into service B, and at that point in time, this request ended up at service B. And from that, you can create this like amazing meshes and figure out how your services work together. And that is actually the original Cleverbit system. So that is how many services we had and how they all work together. But it goes deeper, right? There is a lot of stuff that can be done. And one of the really interesting time series from my perspective is any kind of user behavior. And Netflix is big on that. Netflix collects a lot of information on basically everything you do on their platform, because they want to do things like optimizing your viewer behavior, but also your recommendations, right? It's not like they just want to keep you on the platform as long as possible. They also want to make sure they recommend you content that actually interests you. And that makes sense. And there's a great talk on that. And that is actually a screen capture from the slide. So search on YouTube for Netflix and user behavior analysis. There's an amazing talk about that. They're super open. There's a lot to learn from that. And the last example I want to give is the actual Marvel Cinematic Universe timeline, because that thing is just nuts. Right? So that's all the movies of the Marvel Universe somehow squeezed into a single time series and made readable. Obviously, if you're a major fan of Marvel, that is probably what you do in your free time. I did not. But the links are always somewhere on the slide. I'll share the slide deck afterwards, so feel free to just look it up. It's really insane. So how can we now define a time series? I mean, we've seen a lot of different how to say that, a lot of different examples, right? So from the way that I think of time series is, a time series is a collection of time-related observations for a specific subject, right? If we think about a metric, or a temperature measurement, or an IoT sensor for temperature measurements, we have the sensor, we have a lot of temperature measurements, all with their own timestamp, and they're all put together in this time series to make sure that we can analyze what happened over time, right? That's the time-related part. And that's, from my perspective, the important element of a time series. And that's why you need to optimize, or need to have a database optimized for time series, because your queries and your analytics will always contain this like time relation part. For two examples, I already told that on the actual slide, right? If you have stocks, you have a time, you have a symbol, and you have a price. Or as an alternative, you have like a measurement, you would have something like a device ID in place. So you have time, device ID, as a value or reading that you actually had, and maybe like a location or whatever additional data you need. But when we look at like financial data, we can certainly see like the scope that makes up such an insane time series, right? So the New York Stock Exchange, for example, has 4.2 billion transactions per day. 4.2 billion transactions. And that is just like one day, right? That makes 162,000 transactions per second. And your database need to keep up with that, right? If you ingest that into the database, that certainly needs to be stored, and it needs to be stored fast, because if you drop information, that is not going to work. But the really insane number that I actually cannot wrap my head around is that the New York Stock Exchange in the last 5 years collected 5.4 trillion metrics, or 5.4 trillion transactions. That's an insane number. I don't even know how many zeros there is at the end. I never tried to write down a trillion something, right? Um, so the sheer number of metrics, and if you want to try to analyze, like retrospectively analyze the prices or the price changes of a specific symbol or a specific stock in this case, that you actually have to work on that number of information or that number of data, right? Data records. So why, the question that I always hear, why would anyone sane store a time series in Postgres? And I think there is only one valid answer for that. I mean, Postgres rocks. I mean, seriously, Postgres rocks. Postgres is this like amazing database which is open source, which is extensible. It has a lot of plugins, and you can basically build anything with that, right? You have an extremely established ecosystem. The data storage is rock solid. I cannot say that enough. If you need to store that amount of data or that fast in that ingest speed, you really don't want to lose it just because you have like a failure somewhere in your cluster and all your data is gone because the recovery tools are either not there yet because it's an all new database, or they're not rock solid or not stable enough to actually recover from your database recover the database from the failure. And that is a real issue, right? I mean, imagine you have 5.4 trillion data records and you crash the database for whatever reason, and the recovery tool just fails to recover that. That's nuts. I mean, you may hopefully have a backup, but let's be blunt. If you have like a backup per day, that's good. If you have one per hour, that's amazing. But nobody will go ahead and have one per second, right? So a rock solid data storage is, from my perspective, if you're serious about your use case, you want a database with a rock solid data storage, and none of the new SQL or new databases can actually do that. Period. It's production proven. It's in production for years. It's from my perspective the only open source enterprise database. Sorry, MySQL, not happening. It is SQL. And no custom whatever language, right? It is multi-model, and we will see that. There's a lot of extensions. There is a graph database or a graph model extension. There is a tree model extension. There is document store. There's key value store. There's basically whatever you want, including relational databases, right? And from my perspective, the coolest thing about that, because everything is built in Postgres or as an extension for Postgres, you can join between all those things. It doesn't matter from what data model your data actually comes, or your part of the intermediate data comes. You can just join all of them together. And obviously, the most important fact about Postgres, we all love elephants, right? That's it. No, nothing special about that. So let's go into how we have to store time series, or how time series in general is stored. Not only if we go for Postgres, but if we look at any time series database, they all kind of use the same idea on how to store data, because it is what it is. So the term could be partitioning, it could be sharding, it could be chunking, but don't let yourself be fooled. Don't get scared. It is not as complicated as when you think about sharding in earlier versions, or in the past when you had to go to your database administrator and ask like, hey, can we have sharding in our database? And if they didn't leave the room, you might have been lucky, right? So first of all, what does partitioning or charting or chunking and stuff actually mean? So imagine we have like 10 terabytes of data. We can store that in a single table. And there's people doing that. Databases are fine with that. It all depends on your use case. It depends on the data set you're looking at. But it also depends on like how do we query the data in the end, right? So one option for partitioning is splitting it into multiple chunks and say, hey, instead of like 10 terabyte, I actually have 2.5 terabyte per table and or per partition, and I have 4 partition tables, and they all go up to this like root table that I use for querying and inserting so that everything looks the same. And that makes sense, right? And when you need another partition, you just create another one, and there is another 2.5 terabyte of data. And the only problem is it's 2.5 terabyte of data still, right? That's still a lot of data. So what we want to do is we probably want to go for 1 gigabyte chunks. But 1 gigabyte chunks in the internal Postgres partitioning is hard to achieve, because you need to manually create this partition for every single gigabyte of data. And now imagine you have like, what is it, like 168k transactions per second? What do you think how much gigabyte is, or how much gigabyte that is? It's probably like more than one partition already. But you want to keep those partitions small for the sense of querying. If you later on go ahead and say, hey, I want to query only a specific time range, that is where you can say, okay, I only need like those 5 gigabyte chunks, and I can ignore anything else, right? So the problem is now we have a lot of partitions to create, but the cool thing is Postgres gives us a lot of options to do that. So with the in the past, it depended on how we implemented that, and I'll show that in a second. Right now we have range partitioning, we have list partitioning and hash partitioning in the new partition table. So with Postgres 13 or 14, I think it was 14, Postgres got the new partitioning table, which now has a little bit more automation. And it's much easier these days to create partitions in Postgres, and they're actually much better and much nicer implemented. They have a couple of cool features that we can see in a moment. But those are like the 3 things. So a range partition is basically either a number or a time frame or something like that. A list partitioning is if you have specific keys, like a customer ID or something. You want to make sure that all data for a specific customer reside on a specific partition, because this partition may be on a specific host or on a specific disk, so you can have table spaces and separate out those individual customers. And the last one is hash partitioning. For anyone who ever worked with Hazelcast, that is about what it is. You take like a key, whatever this key looks like, you take a hash code out of it, and you just modulo by the number of potential partitions. That means with enough information or enough objects, you get like a statistically nicely distributed data partition, as long as your data is somewhat close in size, which for normal relational tables is normally a good situation, right? So that is like the 3 options that we have. Why do we do that? Well, there is a couple of reasons why you want these like small tables. I already said it's about the reading, the scanning of the partition, right? If I have like a range partitioning and I have 5 years of data, but I'm only looking for a single month, I only need to select the partitions that hold data for that specific month that I'm looking for. How many tables those are, or how many partitions, I don't know yet, but it may be a partition per month, and then I only need 1 partition, and that means we have smaller tables, right, you have smaller tables, which means you have a nicely faster scanning of stuff. You have smaller indexes, because I already know that I only need to look at a specific table. Obviously, this index only exists on that table, and there is no overall like overarching index, so I can much faster look into the index and figure out what I need to do or what I need to look at, or right, all the records that are interesting. There's something that's called partition pruning. That is exactly this like pre-selection. Hey, I'm only looking for a single month, so I can remove all of the data tables that do not have the necessary information, or that do not fit the time range that I'm looking for, so I can prune all of those from the query. And that is something which was only added recently, but it does an amazingly nice job. And then there is partition detach, which basically gives you an amazingly fast delete. So for example, if you want to retire data, let's say after a year, and you have monthly partitions, you can say, okay, please detach all partitions older than 12 months. That will look if all data in a partition is older than those 12 months, then it will detach it from the overall, like the root table, and then you can just go ahead and delete it. But it's gone immediately, and you just delete it afterwards, right? So those things are incredibly nice, and they make it really nice. So 15 minutes in, let's go for a good demo. We all love demos, right? Okay, so let's see. Can we actually do that? I'm really sorry I created this up front, because a lot of this stuff is I can really not remember from the top of my head. It's really complicated sometimes, but we're good. I created everything up front, so let's actually go for it. We have the create table statement, and we have like a really simple time series database or time series table, right? So we have a couple of measurements, and we store the timestamp on when it was read, and then we have the actual reading, which is the value, whatever the value is we read at that time. So let's execute that. That's a standard Postgres table, and it works exactly like any other table, anything we know. We create a little bit of demo data, so we create 3 different months of demo data with time series every 10 seconds. So let's drop that in. And as you can see, I actually create timestamps in the Japan time zone, because why not? Afterwards, let's actually look at that, right? So we have the table here, and we can see, okay, every 10 seconds, there is an actual reading, and you see that the timestamp stored in the database is in UTC, because that is actually UTC plus 9. So we -9, sorry, it's UTC -9, and we see like some random values for the actual data readings, whatever those readings are. So let's create an index on that. Obviously that all doesn't take a long. That is, I don't know how many elements we actually have here. Let's count them real quick. I have no idea how many we have. So, well, okay, that's roughly 800,000 metrics. And Postgres is fast. Don't get me wrong, right? The standard Postgres stuff is incredibly fast. Postgres 14 did a huge jump in terms of performance again. I'm pretty sure Postgres 15 does as well. So don't get me wrong, right? And here's nothing magic. We have like a standard Postgres table. We create an index, and guess what? Postgres, when we query that and we ask it for the execution plan, it tells us, oh, I have an index, and you ask for like a time range. Cool. Yeah, I know how to do that, right? So it takes the index, it scans the index, and it, well, let's make it a little bit more verbose, so we actually see a bit more what is going on, especially how many records are being returned from that. Okay, let's actually run that on the console. I think that's a little bit easier. There we go. Okay, that's better. So we see that it created, that it actually uses the index that we created. It's on public measurements, and it selected 17,280 rows from this, like, what was it, like roughly 800,000. And it does that by using the index, which is cool. It's super fast in planning. Execution time is nice. The problem is if we go into the million, billion, trillion kind of metrics, it would not be fast anymore. Okay, so that is like the simple version of it, right? As I said, it's just a standard Postgres table. There's nothing fancy about it. So let's look at the second version. So Postgres has an old style of doing partitioning. And it was a little bit more complicated. And just to make sure there's no old database, no old table around. No, it's not. Right? We have the same thing. We just give it a slightly different name. You know what? No, we don't do that. Let's quickly replace that. We're doing the exact same thing just because we can. So we drop the existing table. It's all gone whenever Postgres updates here. Whenever data grid updates, there you go. It's gone. We create the table again, just as we did before. Nothing magic about that. And then we create like inherited table. So those tables, that's the old way, right? So you create tables that inherit from another table the schema, but they also are connected as child tables. So that means we have month 1, month 2, and month 3. And now is the horrible part about this old system, because there was no magic involved to make sure that data actually ended up in these tables. So what we have to do is actually writing a trigger function that takes the record we want to ingest and looks at the timestamp and says, oh, you actually have to go into this table, you have to go into that table, right? So we have one that is here. We see that it tests for the timestamp being between 1st of June and 1st of July. Then we write it to the first data table. If the timestamp is between 1st of July and 1st of August, we write it to the second one. And guess what? If it's between the 1st of August and the 1st of September, we write it to the third one. And to be honest, actually, we should have something like that here as well. Raise exception, time TS outside of valid range, something like that. Because we don't actually have more data tables, and we want to make sure that the data does not end up in the parent table. So we need to make sure that whatever happens otherwise, we actually drop that or raise the exception. So we create the trigger. Now we have our trigger function. Next up, we need to connect this trigger to the actual table. So we could do that, right? Okay, now we have our trigger connected, and the trigger always fires before every single row. So if we want to ingest a row into the metrics table, the trigger fires before the actual row is executed. And what we do is, instead of writing it to the actual table, we actually, before insert on, right, no, sorry, I was quickly just shortly distracted. We return null, which means that the original insert will not be executed. Where if we would return new and just like changed values, we would actually do like a replacement insert, but we return null, so nothing happens. We only execute those inserts that are happening here. Just wanted to make sure that we're not actually inserting into both tables at the same time. Right, so sorry, for every single row we execute this trigger function. The trigger function analyzes the timestamp, does something, returns null, so the original insert that we caught here is being replaced or discarded, better said. Okay, so same thing, we create the indexes. This time we have to create them on the internal tables. That is a little bit on the ugly side. That means, you remember, whenever you need a new partition, a new month, you create a new table over here. You change your insert trigger to have another valid time frame. You create another index, and then you finally get to actually insert your data again. And we're just gonna do that. And it takes a little bit of time, and we're good. And we can, well, let's add the verbose here as well. Verbose. And we execute that again. And the cool thing is that, well, let's actually execute that in the console again. So what we can see is now we scan like the original table where there's like nothing in it, so it's like super fast. It doesn't actually cost anything to do that. And then we see that we have like the free inherited, the free child tables, and they have their indexes. So the index scan just looks it up and it sees like 0 rows returned, 0 rows returned. And here we actually have our 17,280 rows again. So exactly the same thing as we had before. A slightly higher planning time, a slightly higher execution time. That does not mean anything right now because the database is actually not warmed up. If the second you do this a couple of times and the query planner understands how your indexes work, and run some analyze internally and stuff, it will become better. Don't worry about whatever timing is here. We're just messing with the Postgres caches and all that kind of stuff by just throwing away everything over and over again. Right. So the interesting thing though, we see that here is month 1, and month 1 is exactly what we expect. It is exactly what we expect. It's July 1st to July 30th. June 1st to June 30th. The second table, month 2, is actually July 1st to July 31st, exactly as we expect. The third table is also August 1st to August 31st. As I said, if we want to add additional values for September now, we would have to go through all of that again and do all the necessary changes. But for our parent table, we have all the values, and it just doesn't matter if I ask for anything over here. We see that we just access all the data. It's all transparent. And based on that, Postgres created a new version of the partitioning system, fully declarative this time, and we're gonna change that quickly as well, just to make it look nice and obvious again. There you go. All right, so let's drop that again. In this case, it is actually necessary to have the drop table cascade because it tells Postgres, hey, I understand that there is actually child tables or like related tables to that. Just throw all of that away. I really don't care, basically. And it does that, and it takes a second for data grid to update here. And we see that all of those are gone. And now here is a slight change. As I said, they created a new partitioning system. This partitioning system is much deeper built into Postgres itself, which is great. For that, the table that we create this time is not exactly the same, because now we say, hey, we actually want to have this table, but we already tell you that we want to partition that by range, and the range will be our timestamp, which is cool, right? So a lot of work is already being done. We will not have this like create trigger function again. So we execute that, and if we update here, we see that we get this like measurement table. Nothing else will really happen. It just looks what it is, an empty table, nothing fancy about that. Now we add additional tables again, like child tables, but in this case, it is a partition with a specific time range, right? We said we want to partition by range, so we say, hey, here's a table. It's a partition of that table that we just created, and we want it to be valid for the range of, in this case, June 1st to July, up to like end of July 31st, right? So same thing. Then we have July and August. And that's it. It still means we need to create a new partition for an additional month. But this time it is literally as simple as that. You only create that and that's it. And even for indexes, so if we copy this over here and execute this first, I can create an index on measurements instead of the actual tables. And if I do that, that will be inherited all the way down to the actual partition tables, which means if we actually look at the indexes in a second, we see the index over here, and then we see the partitions, and the partitions have the same index, just that it automatically got inherited, which is nice, right? Now we only have a single command that we need to call like on the first of a month, probably a little bit earlier, maybe like on the 30th or on the 31st of the month before, so that with the first value that comes in the morning, we actually have this new partition. But it's also simple to just go ahead and have like an annual job, just creating like a whole year of partitions, because it's just that simple now. And we go ahead and we insert our data again, just as we did before. And it's taking a second, and we add our both here again, just because I really like that. And let's turn it off for now, right? So you remember partition pruning, it's possible for the database to say, hey, I understand that query and I understand what you're trying to do. So I can remove all the necessary tables. And something is wrong here. It did partition prune. Huh. Wait a second. Am I not able? Forget it. Right. My fault. Obviously, if you do it that way, if you do it that way, it only counts for that specific session. So it will count for that database session in data grid. It will not count for that partition, for that session. So if I do it now, okay, there you go. Then we have like the 3 different indexes, and we see 0 rows, and here's our 17,280. So if I return that or revert that and say, hey, partition pruning is actually activated, it does exactly what it did before. It already figured out, hey, I only need to look into one specific partition based on the range, and return this like 17,280 rows straight away. And it understood that because of the data range, and because Postgres understands how to analyze this data range and how to say, hey, those partitions will not contain any data based on the range or based on the customer key, like with the list partitioning. So I can just remove those from whatever is happening. So that's nice. But I want to show one more way, since we are actually, because I'm working for timescale, and because I really like timescale. So from my own startup, as I said, I use timescale quite a lot. That's the reason why I ended up here. I really loved it. And I still think it's slightly more convenient, in the sense we still create this like specific table, right? We still have our measurement table. And let's remove that for a second, just for the jokes, and or let's do that, right? So let's do the same thing. We have the measurements table created. It is here, and it looks exactly like we expect it to look like. Then we have this like magic function that you only need to execute once. It's create hypertable. Like take the measurement table with the time column, which is TS for timestamp, and we tell it to create chunks with 1 month of data. So if we execute that, we get like an interesting return here. It is preferred hypertable. I played a little bit around with that. It's in public schema. It's called measurements, and it has a timestamp, whatever the last column is. To be honest, I don't even know. All right, so now we need to refresh, because data grid does not understand that we actually changed the schema of this table. But if we force it to refresh, we see some magic happening here, right? So what we see is that we get some things which happen automatically. First of all, we get this like measurement TS index. So we automatically get this like timestamp index that we created up in the other tables, because timescale understands, hey, we are actually talking about the time series now, so obviously we need this index. But it also creates like a TS insert blocker, which kind of works like the function we wrote before, like the trigger function. But it is all handled automatically for you. And the rest of the stuff looks just standard, right? So we don't need to create the index. That's done for us. We insert the data. And while this is happening, we can fix that again already. We do not care, and that's important, we do not care for partition pruning. That has nothing to do with timescale. For timescale, that always happens. So if I do that, we see that we actually have a hyper table, number 3. We are in chunk 108. I don't care. Who cares? We see that we have got 17,280 rows returned, and we see that timescale automatically understood, hey, whatever this chunk is called, or whatever the time range is, I only need this single chunk. All right, so that was fun, but let's go a little bit crazy here. Something that you would probably not do with the variations we've seen before, right? Right now we had like a hyper table of 1 month. So let's recreate this table. And instead of saying 1 month, we're going for a single day. We're just being nuts here, right? We wait for, there you go, for your data grid to finish up. We force to change it again, to reread the data table again. And we see that it will add the index and the trigger again. Same thing, nothing fancy happens here. And we're gonna insert it again. Who cares, right? The cool thing is, timescale does all of that. It automatically creates those like 1 day chunks. That means if I gonna execute the same query again that we had before, you remember in the first run we had like 1 month chunks. Now we have daily chunks, so I should see like 3. I should see 3. Do I see 3? Oh no, sorry. I see 2, obviously, because I stop on the end of July 15th. So obviously that means it actually understands that there is only 2 chunks. It does not use the index scan in this case, because we actually need all values from both chunks. So the query planner figured out, hey, I can do a sequential scan. I don't need the indexes because we don't have like additional criteria that we need to take care of. All right, so that's cool. And timescale did all of that automatically. And just for the laughs, let's look, because what we have here, and even if I force a refresh, we still only have this like 1 table that we can see here, right? And we see that we still have only this like 1 table. So how does the magic work? In timescale, we actually have a specific internal a schema where we hide all the necessary magic from you, because you ask for a single table. So why would we tell you, oh, we create like 1 million tables underneath? Because why would that be of a bother of you, right? So you see here, we have all of the hyperchunk tables, and this time it's hyper table 4, because you remember we deleted and recreated it, and the chunks get counted up. And that is actually the tables that create or that contain the data. And you can see it's like July 19th. If we go for the next one, it's July 20th. And so on and so forth, right? So the beauty is that timescale does all of that automatically. You don't have to bother with anything of that. You don't even have to think about that there is tables underneath, because timescale, just like all the other ones, just makes it possible to query all of that, right? So you see we have August 31st, we have June 1st, It just doesn't matter. It all works as expected. All right. With that, let's try to get back here. Where to go next? There's a few things. We have a really nice blog post like what is time series data. We have a really interesting, if you're in NFL or anything like that, we have a really interesting data set that you can use and try out for playing around with stuff. Trying to figure out how timescale really works. We have a lot of additional information, a lot of additional functions that are specific to time series, specifically when you want to read or analyze the data into buckets like daily buckets, weekly buckets, maybe hourly buckets. We have functions to make this easier. There is a really interesting blog post on time series forecasting. So like data prediction based on historic events. And in general, I can always tell you, look at the docs. The docs are really amazing. It is not that I say you actually have to use timescale because you've seen it works otherwise. But my claim is, if you want to do it easy, take timescale and be good with that. It's free. You can just use it. We have Timescale Cloud if you're looking for a managed service. And with that, I say thank you very much. Arigato gozaimasu. And I hope there is a couple of questions for the discussion afterwards. Thank you very much.